Hello. My name is Jawan Kim, and this is my lab to line of charge. To introduce this lab, the purpose of this lab was to calculate the electric force based off the charge tapes. And the purpose was that the purpose of the lab is to investigate the electric forces between the two charge tapes and to understand the principles of electrostatics. And I'm just going to explain the code, the physics behind this, and the vocabulary behind it using the code. So basically, the first thing that I had to edit from the code was adding the code from the first lab, which was basically the simple E field equation, which I have shown here before. It's E equals KQ over R squared multiplied by R hat. And I have successfully done that by adding that into my my code. R equals observation location minus the charge particle minus dot position. You get the position. R has the R minus the magnitude of the R, which R in this case would be a vector. And E multiplied by pes, which was a 9 to the 10 to the ninth, multiplied by the charge, divided by magnitude, the 2 hat multiplied by R hat. And that whole function returns the electric field. And the second part where I had to edit the code was actually quite simple. So this code defines a function, line charge, to create two tapes presented as a line of closely spaced point charges. These point charges have a distributed charge along the length of the tape. The function calculates the electric field due to each individual point charge. So yeah, so electric field vectors at each point charge in top tape due to bottom tape are visualized using the arrows. Um, and then it gives me the net electric force and gravitational force due to on top tape due to gravity. And those are the codes that I had to edit in. And as a lab report results, this is the last graphic that I got. I have had to scale to a very, very small number to make it show properly. The magnitude of the charge on one piece of tape as calculated in my computation model was 3.33352. And the assumptions and the approximation and the idealizations I had to make was the fact that air resistance was clearly ignored because it was not a factor in the code. And the code also reflected that tape has some same amount of charge evenly distributed throughout and the whole length. So this is where I think a possible error can come in compared to the real life, because code models the tape as collections of discrete point charges with equal spacing, which is a simplification. But in reality, charge distribution on tape can be continuous or non-uniform. This simplification may lead to inaccuracies, especially if the charge distribution is not uniform, which is most of the cases. So let's answer what if and why. So what if you have modeled blah 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 blah? If me using the point charge, so I just used the top tape as 1 point charge, bottom tape as 1 point charge, and by using that, I got a magnitude of 5.76 to the sixth, 10 to the sixth, and that is larger than what I got, which was 3.33. And why do these estimates differ? It's pretty obvious why it differs. And the line of charge is obviously more likely to be closer to the real value because it considers the distribution of the charge along the tape, which affects how electric field varies with position. In a practical scenario, charges are spread out and the spatial distribution matters. But again, that's I already said that the point charge model oversimplifies this distribution, leading to the less accurate results. Thank you.